Welcome to this section. Now, moving on from these definitions, now I'm going to cover the class of fire. What extinguishers can be used on different types of fire? That's what I'm going to cover now. So what are the classes of fire? There are 5 classes of fire. The first one is a Class A fire, which is normally involving solid materials of an organic nature like wood, cardboard, paper, fabric, etc., in which combustion generally occurs with a formation of glowing embers. You've got Class B, which is fires involving liquids or liquefiable solids, for example, oil, petrol, diesel or paint. A good example of a liquefiable solid is cooking lard, which at normal temperatures is a solid, but as soon as it's heated it turns into a liquid, so it's classified as a liquefiable solid. Class C is gases. LPG, propane, butane. Now remember that extinguishing a gas leak which is on fire may actually result in an explosive atmosphere building up within a confined space, as long as it gets above the LEL. If sufficient heat remains or a spark is introduced, the flammable mixture may reignite with serious consequences for yourself and the building. You'll get an explosion and fire. Class D is fires involving metals. You've got sodium, potassium, magnesium, plutonium, titanium. All these are flammable metals. Now, extinguishing agents containing water are generally ineffective and even dangerous. Carbon dioxide and general purpose powders may also be hazardous. Therefore, there are special extinguishers which are designed specifically for use on metal fires. We will come on to this later on. Class F, cooking oils, deep fat fryers. Now these are difficult to extinguish due to the high temperatures. You might get up to 450 to 600 degrees with these. What about electrical equipment? If anything electrical catches fire, what's the first thing you should do? Isolate, turn it off. However, some electrical appliances have a capacitance. They can store a voltage, store a current. So you might think you've turned it off. If it's got a capacitor in there and you put water on it, you will still get a shock. So even if you've isolated, you can only use what type of fire extinguisher on electrics? CO2 or powder. Do not use foam. There are some that call them tri-class foams. However, now, even they've said now, really, you shouldn't be promoting using foam. Because it's water-based on electrical equipment, you should use CO2 or powder. If not, you'll look like that. You know, the morning look. So let's go again, what you can use on these suitable MIDI for classes. Class A, solids, you normally use water in the form of jet or spray. But you can use foam and you can use powder. You can't normally use CO2 on a Class A fire because if you put a CO2 on a bin fire, what happens to it? It just spreads it. Class B liquids, you normally use foam, CO2 or powder. Now the foam they use nowadays in all these extinguishers is called AFFF. And that stands for aqueous film forming foam. It forms a film on top of the fuel. Now say that after a few beers. It's aqueous film forming foam. It forms a film on top of the fuel. Or you can use CO2 or powder. Do not use water. Class C, well, the only effective action is to isolate the supply. So gas, you isolate. Powder will put it out, but then you've got a gas leak. So if you're going to put it out, you make sure you can turn it off. Generally, gas, you isolate. Class D, a special extinguisher is required. You've got powders such as TEC powder, which is ternary eutectic chloride. How does it put out a fire? Well, it forms a crust. These magnesium powders, etc., are getting very, very hot. That's why you can't put water on them. You put water on them at high temperatures and it turns water from H2O into hydrogen oxygen and explodes. That's why you use special powders, TEC powder. It fuses around the magnesium or whatever metal it is at about 450 degrees. It creates a crust and it effectively extinguishes the fire. Or there's another brand called M28 or L2. You can use dry sand, if you can find any, or earth. Graphite powder can be used, sodium carbonate and salt, and you can use talc. Graphite or powdered limestone. So there's a few you can use on these. Now this video shows you what happens when you put magnesium with water. This is what happens. That's how volatile it is. What about lithium in water? Let's watch this one. This is lithium in water. You put lithium in water, you look what happens. Rapid oxidation, and it can be quite violent. The next is Class F, deep fat fryers. How do you deal with a chip pan fire? Well, people always say you get a damp tea towel or a fire blanket, place it over and turn the heat off, yeah? Is that what you do? When do people most fancy chips? When they've had a few drinks. They get back, I fancy some chips, put a chip pan on, put a video and fall asleep. When it catches fire, what do they normally do with it? They pick it up and run round the house showing people it. What do I do? What do I do? Chip pan fires are the worst type of fires. We had one guy, he opened a window on a windy day and he threw a chip pan full of oil through a window on a windy day. What happened? It blew back all over him. We've had loads of cases. When I was in the fire brigade, I was in the Defence Fire Service. I managed to get a 3-year tour in Cyprus in the Air Force. And when I was in Cyprus, the chief fire instructor went down Limassol for a few beers. He got back 3 o'clock in the morning. I fancy some chips. He put a chip pan on, put a video on. What happened? It caught fire. What did he do? This is the chief fire instructor. What did he do? He picked it up and he ran through his house. Ran through his house and threw it in the garden. Is that a good idea in Cyprus with all the bondo? And he thought, I've sorted it out. He turned round, his house was on fire. He had to call out the fire brigade. How embarrassing was that then? He called the fire brigade out. I was on night shift that night. And you know, I just want to point out one thing to you now. You do know that firemen do not sleep on night shifts. We do not sleep. We rest our eyes in beds. It's horizontal resting, not sleeping. I was on night shift, the alarm went off, ran downstairs, got the printout, looked at it. I said, wait there a minute, that's Jim's house. That's the fire trainer's house. What did we all think? We thought it was a practice. We thought the sad person, look at that, 3 o'clock in the morning, calls a practice. You play the game, you play the game. We turn up, we got there, there's flames coming out of his house. We thought, that's effective. We went in, we put the fire out, he came over, he said, lads, come here. You're not going to tell anybody, are you? Would we tell anybody? All I'm trying to point out to you is, when chip pans catch fire, people panic. They run round the house. That cooking oil is at its auto ignition temperature, which, if you remember, is 450. 450 degrees. When it's burning at full intensity, what temperatures does it get to? 600? Can you imagine what cooking oil does to your skin? We've had people putting their arms in, trucking chip pans out and covering themselves on fire. There's a special extinguisher designed for it. It's called the wet chemical extinguisher, and it's made up of potassium acetate, carbonate or citrate. Now, these extinguishes the fire by forming a soapy foam blanket over the oil, which is called saponification, and then it lets it cool below its auto ignition temperature. That's the only way you're going to put out a chip pan fire, is to cool it below its auto ignition temperature. Now, watch this video. This is what happens if you put water on a chip pan. Watch this. He's going to put some water on a chip pan. Watch this. It explodes. Why? Because the oil's at 450 minimum, the boiling point of water is 100, you put it in, it explodes. That's why it turns into steam. There's a special extinguisher which has gone through that puts it out by saponification. And this is an example. This cooking oil here has been ignited, but it's at the moment it's 306, just start ignited now. Obviously a different type of cooking oil. What it's going to do, this guy here, is going to take the heat away from the fire. Take the heat away. Gets the fry fighter extinguisher out. Now watch how quickly this puts this fire out. Class F extinguisher, wet chemical, straight out. It puts the fire out very quickly by saponification. They do recommend you keep putting it on. It's specially designed for deep fat frying. This fire blanket business and damp tea towel business only works if you're in the kitchen at the time. If you've got a chip pan fire, you walk out and the chip pan's going and you get a little Scarborough tea towel with a smidgen of water on it, is it going to put it out? No, it only works if you're in there at the time. Well, first of all, fire spread is exponential. What does that mean? Well, it's a chemical reaction. What it means is, after double the time, the fire will not be double the size, it will be 4 times the size. After 3 times the size, 3 times the time, it will not be 3 times as big, it will be 9 times as big. That's what exponential means. Now, fire can spread in 4 ways. There's 4 ways a fire can spread. Firstly, you've got conduction, convection, radiation, and direct burning. Let's go through convection first then. This is the most common cause of fire spreading buildings, convection, hot air ride. The most common cause. Now, it can only occur in gases and liquids, not solids. So solids can't have convection. Convection is the main cause of it, and it's due to the fact that hot air is less dense than cold air. Because did you know that air weighs something? Now, just to be fair, just put your hands like that. Put your hands like that. And can you feel the air in your hands? Does it feel heavy? People do that and they say, it's hard to tell. I think that's my hands. Air does weigh something. If you went outside now and got all the air from 1 square kilometre, all that air, brought it in a room and compressed it all, how much would it weigh? How much do you think the air would weigh? People say, I don't know, not a lot, not a lot, not a lot. Well, I'll tell you how much it'll weigh. 10 million tonnes. Air possesses mass. Did you know that 1 metre cubed of air at ambient temperatures, 1 metre cubed of air, that bit of air, weighs 1.2 kilo. That is the density of air. 1.2 kilo per metre cube. That's the same as half a bag of sugar. Half a bag of sugar. Now, what happens if you heat air? So the fire heats the air. Well, it expands. Well, if it's expanding, what's happening to the density? It's being reduced. It's becoming lighter, less dense. That's why hot air rises. Because the air is less dense. Hot air is less dense than cold air. And it rises. Now, did you know that all gases expand at the same rate? All gases expand by 1 at 273rd of its volume at 0 degrees C. So, if you increase the temperature of a gas by 273 degrees than what it was at 0, what's the density? Well, it's halved. What temperatures do you get in fires? 600 degrees is flashover. You can get temperatures of 1,000 degrees. Well, if you heat air up to 1,000 degrees, it's now about a quarter of its density that it was at 0 degrees. So convection is due to hot air being heated, rising, less dense, and as it travels away, it starts to cool and it starts to come back down again. That is why you normally see the pattern hot air rising, convection. In a fire, the convection currents can carry hot gases upwards through stairwells, open shafts, and it spreads the fire by taking embers as well. When reaching the ceiling height, it spreads laterally, it starts to go away. And what happens? Basically, how do you prevent fire spread due to convection? Well, you compartment buildings. Compartmentation. You can use fire separation. Fire stopping openings. Don't let the fire get through openings. You can use fire-resisting doors. And finally, fire-resistant walls. So that covers convection. So don't forget, convection is hot air rising due to being less dense than cold air. As it travels away, it's heated. It's replaced by cold air, which gets heated, and that travels up. And as it travels away, the air loses its heat and it starts to come down. The next mode of heat transfer I'm going to cover is radiation. Now, radiation is the main cause of external fire spread. Not internal, external fire spread. And it can be described as electromagnetic heat transfer, and it's basically infrared radiation. It travels in straight lines. Radiated heat travels in straight lines. Now, do you think radiation can travel through a vacuum? Well, what heat do we get from the sun? Radiated heat. It's travelling through a vacuum. Yes, you can. Now, fires caused by radiation can travel through a glass window. Can travel through a glass window and spread fires. So that's why if you wanted to build a building, that's why there's boundary distance in buildings. Buildings are not allowed to be built too close to the building because of radiation. Radiation was the main cause of fire spread in the Great Fire of London. That's why the boundary distances came in. Because there was a fire in London at the time, the houses were too close together. There was a fire on one side of the street, the radiated heat travelled across the road and it spread the fire. Did you also know that the intensity of radiation in a fire is inversely proportional to the square of the distance? Did you know that? What does that mean? Inversely proportional. What it means is, if you half the distance, it's 4 times the intensity. If you've got a fire and there's a cylinder being heated in a fire 5 metres away, and it's 1 unit of heat at 5 metres, what would the radiation intensity be 1 metre from that fire? So at 5 metres it's 1 unit, what's it at 1 metre? What you do is you flip it over, it's 1/5 of the distance, flip it over, which gives you 5 over 1, and you square it, 5 times 5, 25 times the intensity of radiation. Do you understand why these distances, where you should store skips away from buildings, get them away? Because that's the principle. If you put things too close, the radiated heat is massively intensified, and that's the main cause of external fire spread. How do you stop fire spreading from radiation? Well, physical space separation. Get them away. How far should you store ignition sources from cylinder? As far away as you can. And if you can't, you use physical barriers. So you put a physical barrier there instead. Fire brigades, when they turn up, how do they protect cylinders in a fire due to radiated heat? We put spray jets on them, with sprays on them to protect. The next heat transfer mechanism I'm going to go through is conduction. So I've covered radiation and convection, now conduction. Conduction is the transfer of thermal energy between neighbouring molecules in a substance due to there being a temperature gradient there. And it always takes place from a region of higher temperature to a lower one. It's always transferring from higher to lower, and it acts to equalise. Let's say now I've got a metal bar in my hand, yeah? Now that metal bar, if you looked at those molecules in the microscope, they have all got kinetic energy. They've all got, those molecules have got kinetic energy and they are vibrating. You can't see it, but that molecule is vibrating. And that's at normal temperatures. If you heat that bar up at one end, what happens to the kinetic energy of the molecules at that end? Well, it increases. So the molecules at this end are going like this. And the molecules at this end are going like this. Now, good conductors will allow the kinetic energy of those molecules, that heat to travel down them. So that's what conduction is. It's the kinetic energy molecules. A good conductor will allow it to travel down until it equalises and the bar becomes the same temperature. And that's how fires used to spread, due to conduction. You've got a metal bar going through, a metal beam going through a building with a compartment walling. If there's no fire stopping, the heat will travel straight across the fire. That is what conduction is. And it can be relevant to solids, liquids and gases. Again, like I said, if you hold a metal bar, that's what happens. Good conductors are metals, so silver and copper, for example. Poor conductors, wood, cork, glass, asbestos. So if I got a lump of wood, the molecules are vibrating. If I heat up one end, what happens to the molecules at that end? They vibrate more. But poor conductors will not allow that transfer down the wood. Think of a steel door, that's why you fill a door for heat, don't you? Due to conduction. How do you prevent fire spreading from conduction then? Well, for example, a steel girder across a compartment wall must fire stop it. So basically you put something in between that's a poor conductor to stop the heat travelling across. You can insulate structural steel with fire resistant materials to stop the heat getting to it. Originally they used to do it with asbestos, but we know the problems with asbestos. Now they use spray mineral coatings and dry linings. The last heat transfer mechanism I'm going to cover is direct flame impingement, which actually is a consideration of the other three. So basically, direct flame impingement, in a way, is the flame directly touching it, is a combination of all the other three. Let's just summarise fire development. I come in here and I set fire to a chair. As you set fire to a chair, what's the first mode of heat transfer? Up. Hot air rises due to convection. The hot air is expanding, it's rising. That's convection. When the hot air reaches the ceiling, if it was a metal floor and you're stood above it in bare feet, what will happen? Well, the heat's going to travel through the metal due to conduction. So the person above it will be going, my feet, my feet. Now, as the heat travels across the room, what heat's coming down? Radiation. So as the hot air travels across, you'll get radiated heat being travelled across. Now, as the hot gases heats the radiation, what happens as more gases come across and it starts to go down and down and down? What happens to the intensity of radiation on that table, for example? Inversely proportional to the square of the distance? Can you appreciate, as it's getting lower and lower and lower, the radiated heat is travelling down, it's getting much more intense, those materials start to decompose, pyrolyse and give off vapours. Eventually there comes a point where the whole room goes up. And then you've got the whole room involvement, which basically is a flashover. And that's what I'm going to cover later on. That covers fire development. Now I want to discuss the stages of combustion. Let's have a look. Fire development depends on a number of factors. You've got to take into account the room geometry, the ventilation of the room, fuel type, and the amount and surface area of the fuel. They're the factors that come into it. Now, fire is often discussed in terms of the temperature development and can be divided into different stages. And all this is relevant later on with the course on how detection is carried out. As you can see on this chart here, firstly you get induction and followed quickly by ignition. Then you've got your growth phase depending on the type of fuel and the ventilation conditions. Next issue you're going to get is a flashover. That is followed by a fully developed fire with maximum heat release, maximum temperature, and then you get your decay phase. Let's go through these now. Induction, the first part, the chemical reaction of the ignition process has taken place. It's basically you're heating it up, it's spiralising, decomposing and giving off the gases. Now the temperature within the area will rise, and if there's a significant rise in this temperature, other materials become involved and the fire will start to grow. This brings in the growth phase. Now, during the growth phase, the temperatures rise dramatically depending on the heat release, and the involvement of all materials within the room eventually become involved. And this could be over a short or a long period of time depending on the fuel. Now, in fire safety, it's not the amount of heat that's given off that's important, it's how quick it gives it off. So that is why the heat release rate is important. It's how fast it gives it off. And this is the fire growth rate. Now, this chart here shows you the heat release rate against time of some materials. For example, a solid wooden cabinet will burn with a slow growth rate. Upholstered furniture will burn with a fast fire growth rate, and thin plywood wardrobes burn with an ultra fast fire growth rate, as you can see on this chart again. Now there comes a point in the growth phase at which a certain temperature is reached, and normally this is approximately 600 degrees, at which the whole room becomes involved, and this is a flashover. Now the flashover, the definition is a stage in a compartment fire when the total thermal radiation from the fire plume, the hot gases and the boundaries cause the generation of flammable products. In other words, everything's heating up and giving off gases, pyrolysing, from all exposed combustible materials within the compartment. So that's giving off the conditions. Given a source of ignition, or if it reaches its auto-ignition temperature, this will result in the sudden and sustained transition from a growing fire to fully developed. In other words, following your flashover, you've got a fully developed fire. After flashover, the temperature plateaus, and this is the highest temperature you're going to get in that compartment, and it's normally about 800 degrees. Then, as the fire starts to decay, after this phase, a stage comes when the fuel becomes consumed and the energy release diminishes, and thus the gas temperature will decrease. In other words, the fire will start to go out. Now, if the fire starts to run out of oxygen, it starts to go down the temperature. But what happens if somebody opens a window or a door? What can happen is a backdraft, and this can happen again, and it goes back up to a fully degrowth fire with another flashover. So during this stage, the fire goes from a ventilation control fire, because there's loads of oxygen, to a fuel control fire. In other words, until all the fuel is consumed, it will continue burning, because this is due to the available fuel being used up or the available oxygen pipe being exhausted, which again, like I say, could lead to a backdraft, which I'll come on to in a bit, or the intervention of the fire brigade turning up with putting water on it. Whatever the intervention or reason, there will be a remarkable decrease in the temperature, and eventually the fire goes out. That is the stages of combustion. Now that covers fire development and stages. Let's move on to what kills most people in fires. Smoke. That's what kills most people. People do not die in fires from burning to death. They normally die from smoke. What do they do in the movies? What does Bruce Willis do? He gets a wet hanky. Have you noticed that? A wet hanky, and he walks around. Follow me! Come on! Does that work in a fire? Does a wet hanky work? Of course it doesn't work. It filters some of the gases, but it does not... If I set fire to a chair now in a room, do you know how many gases it'll give off in a fire? How many a chair will give you, roughly? 600 different gases. Have you got a pen? I'll tell you them all now. Hydrogen cyanide, you breathe it in, a couple of whiffs of it, down you go, 3 minutes and you're brain dead. Hydrogen chloride gas, you breathe it in, it burns your lungs filled with water, down you go, 3 minutes and you're brain dead. Carbon monoxide, you breathe it in, a couple of whiffs of it, down you go, 3 minutes and brain dead. You do not have to have substantial amounts of smoke to die. If you're walking down the corridor and there's smoke in that corridor and you carry on walking down there and there's all these toxic gases, you breathe them in, down you go, 3 minutes and you're brain dead. That completes this section of this element.